Assalamu alaikum, dear students. Welcome to the 7th program in the operating system lecture series. And today we plan to discuss the memory management. Dear students, you will recall that we have some basic knowledge of memory. In our previous sessions, we discussed components of the computer and we discussed primary and secondary memory. We also briefly discussed memory hierarchy, in which we touched upon the registers, cache, main memory, disk, tape, and we also discussed the memory partitioning while we discussed the memory multiprogramming concept. We briefly discussed that memory management is a feature of operating system. We discussed process registers, in which we covered the user visible registers and status and control registers. Dear students, today we plan to cover and expand on our previous knowledge on memory management. We'll look at monoprogramming, modeling multiprogramming, multiprogramming with the fixed partitioning, and multiprogramming with dynamic partitioning, memory management with bit maps, memory management with linked lists. We'll discuss the concept of swapping, virtual memory, concept of paging, and page replacement algorithms. Now let's look at the concept of monoprogramming. This is fairly old concept and was used in the initial days of the computer. It's no more used any longer, but for the sake of a comparison that where it used to be and where the memory management is today, we'll briefly discuss the concept of monoprogramming. In the monoprogramming, as you know, that apart from the operating system, along with the operating system, there is just one program that could be held in the memory. Let's look at the diagram, how the monoprogramming actually functions. In this diagram, we see the one part of the memory is occupied by the operating system, which is in the RAM, random access memory, and remaining complete chunk of the memory is one user program. Another alteration of this could be the operating system in ROM, read-only memory, and a remaining memory portion is occupied by the user program. Or yet another variation could be that operating system is in RAM while the device drivers are in ROM and the user program occupies rest of the memory. And in this, one thing is very clear, that this is not an efficient use of the memory. Gentlemen, what do we conclude from this? We conclude that monoprogramming is an inefficient way of using the computing resources, memory as well as CPU, because when just one program in the memory, most of the time CPU is waiting for input or output, and this is not efficient. Now let's see how the CPU utilization improves with the degree of multiprogramming. We'll look at with the help of a diagram. In this diagram, we see the degree of multiprogramming 1, 2, 3, 4, 5, 6, and n number of processes coming in the memory, and on our y-axis we see the CPU utilization. In fact, the CPU utilization is a function of degree of multiprogramming along with the percentage of time the I/O wait for a particular process. If we have 20% I/O wait with less number of programs, we can achieve higher degree of CPU utilization, so much so we can reach up to 100% of the CPU utilization. If our I/O wait increases to 50%, we need more number of processes to be present in the memory. If our I/O wait further increases to 80%, this curve shows us that we need even larger number of programs to to achieve high degree of CPU utilization. And the last curve we see here is at 90% I/O weight. If our processes are highly I/O intensive, then we'll virtually need large number of processes to achieve higher degree of CPU utilization. Gentlemen, this leads us to a conclusion that higher degree of CPU utilization is desired, large number of processes availability in the memory is desired in order to get higher CPU utilization, in order to efficiently use the system resources. Now the question is, how do we do it? And once again, the answer is multi-programming. We partition the memory in multiple partitions, and in each partition we run an executable program or a process, and as such we achieve higher degree of CPU utilization. How it's done? Now let's look at a diagram and explain how the memory is partitioned and how the programs are run in various partitions. We have two ways of partitioning the memory. One is we partition the memory in fixed size partitions, and other is dynamic partitioning. Now let's look at the fixed partitioning in multiprogramming. The multiprogramming with fixed partitions. In this diagram, we see that our memory is of 800K size, which is divided into number of partitions. First 100K is allocated for the operating system. The second 100K from 100 to 200K is for partition 1. Our next partition is from 200 to 400K. It means it is the partition 2 is 200K. Our partition 3 is from 400K to 700K. It means our partition 3 is equivalent to 300K. Here we see partition 4 starting from 700K ending at 800K. It means our partition 4 is equivalent to 100K. Now, once we have fixed size partitions of our memory, we have to queue the jobs to be run in these partitions. We see these 3 jobs queued in front of partition 1, 1 job queued in front of partition 2, there is no job queued in front of partition 3, and we have 2 jobs queued in front of partition 4. It means when the existing job in the partition 1 is completed, the next job in the queue is serviced in this partition. We have 2 problems in this schema. One problem is that let's say this job requires 75K, okay, but our partition is 100K. When this job lands up in this partition, the remaining 25K of the memory will go unutilized. This is one limitation in this queuing scheme and in this fixed size partitioning mechanism. Another problem, we see a fairly large size of memory partition, 300K, there is no job in front of that. It means we are also losing, we are not efficiently utilizing this memory because this is there is no job queued, while the smaller size partitions have queues in front of them. What do we conclude? That this is not an efficient algorithm to queue the jobs in front of the fixed size partitioning, and this is not efficient utilization of the various memory partitions. An alternate scheme is we queue all the jobs in a single queue, as we see here, all the jobs in a single queue, and whenever a partition is free, we send the job to that partition. Okay. Now here again we have some problems, and that problem is that a small size job, let's say this job is of 200K and the only empty partition is partition 3, then this job will end up in partition 3. It means that our partition 3, which is 300K, is underutilized by 100K. This is again not an efficient way of memory partitioning or memory utilization, and the queuing algorithm is not very efficient. So what do we do that with this? What we can do is that if there is a small job, we put that small job in the wait state. I think that will not be, in principle, that will not be correct, because the smaller jobs are required to be given better service instead of smaller jobs putting on hold. What is the solution to that? Solution to that is that whenever a smaller job is, there is a likelihood that a smaller job will end up in a larger partition, we hold that job and give that job some points. And maybe in the next go, if that larger partition is still empty, we give that job still some more numbers. When that smaller job accumulates certain points, then nobody could hold that job, and that job ends up either in an appropriate size of partition or in a larger size of partition. Then the operating system will not further withhold that particular job and will not discriminate. From this diagram and from our discussion, we conclude here that despite the fixed size partition improve our memory utilization and CPU utilization to certain extent, but still it is inefficient, because matching the job size with the partition size, with the available memory partition size, is not an easy task, and certain part of the memory still goes unused. Now the point is, what should we do? There is still a little more efficient algorithm to be utilized for efficient memory utilization, as well as obviously for a good CPU utilization, and that is multi-programming with variable size partitioning. How it works? Let's look at the diagram. In this diagram, we see at any point of time A, B, C, D, E, F, and G, we see at point A, this is the situation in the memory. We have operating system here, we have job A in the operating system, and this yellow portion, this is the empty portion of the memory. Now we receive another job, and that job lands up just after A lands up here, and certain more memory is allocated to job B. Now at point C, we receive another job, and that job ends up in the remaining part of the memory we see here, and now we have less amount of memory remaining. And in this way, we keep on, the jobs keep on coming, and we keep on allocating the required amount of memory, and once the job is finished, then we bring that memory vacated by that particular job, and we bring that memory to the pool. We see here the job A is completed, and now we have this part of the memory is empty, and this part of the memory is empty. At next instance, we receive another job D here, and since the remaining portion on the upper part of the memory is not sufficient, we allocate the amount of memory spared or vacated by process A, we allocate the memory to process D. Now at the next instance, we see the process B is completed, and that part of the memory is again becomes a pool of the available memory, and D continues. Now we receive at another process E, and so on. From this diagram, we have seen that this is definitely a dynamically allocating the memory is certainly an efficient way of doing it, of dealing with the memory, because the number, sizes, and locations of the partitions, it varies based on the need. As the jobs come and go, the number, size, and location of the partitions, it varies and it changes. But this again has certain limitations and complications. Number one is that we have to keep track of what part of the memory has been allocated, what part of the memory is vacant, and when certain part of the memory is vacated by a process, we have to bring it back to the memory pool. And that is fairly a complex task. Allocation and deallocation of the memory is fairly complex task. One other limitation in this schema is that we allocated a part of the memory to a process, and then we receive another process, we allocate certain memory to that process. What if a process wants some more memory for expansion purposes, for some more data, for some more stack? How do we do it? This algorithm does not serve that purpose. So what do? The experts have created another algorithm where when a process is allocated the required memory, certain more memory is allocated to that for expansion purposes, because it is impossible to determine in advance that a process requires some more memory for expansion purposes or not. And at the very beginning, the operating system decides and allocates the memory, a little more memory than the required. How it is done? Now let's look at a diagram. In this diagram, we see that one part of the memory is occupied by the memory, and we see here that this part of the memory is actually in use by process A, and certain more amount of memory has been allocated to this process for, and that is essentially a room for growth. If a process A wants to expand, then memory is already available. Similarly, we have process B. This portion of the memory is actually in use, and we have some room for growth. Now, room for growth, again we have a more efficient algorithm to allocate this room for growth. We say, let's see in this diagram variable partitioning B part. We see here that the A is further subdivided into program, partition for A data, and partition for A stack, and the partition and the remaining memory in between the A stack and A data is the room for growth. And there is I think it is a tricky allocation, very intelligent, because if data wants to grow, data can grow. If stack wants to grow, stack can grow. And if still we run out of memory, we have to take all this program, data, and stack to a different location. But this is certainly an efficient algorithm of memory utilization. Dear students, we saw that this dynamic allocation of the memory for program, for data, and associated stack with some space for expansion is certainly an efficient way of allocating the memory. We briefly alluded in our discussion previously that there is one complication. We have to allocate and deallocate the memory, and we have to keep track of the memory, which part of the memory is currently being used, which part of the memory is being spared by a running process, and then bringing it into a pool. This is fairly a complex process, and we need very well developed algorithms to manage the memory. And we do that memory management with the bitmaps, memory management with linked lists, and memory management with buddy lists. We'll discuss briefly memory management with the bitmaps and memory management with linked lists. Now let's look at how the memory management with the bitmaps works. Let's look at a diagram. We have a process job A, B, C, D, E, and then in that part of memory we have certain holes or empty parts. We see here in this color, this is empty, this part is empty, and this part is empty. And we see in this essentially schema, the memory is divided into allocation units. And the size of the allocation units can vary from a few bytes to few kilobytes to many kilobytes. We see here that from 0 to 5, these 5 allocation units have been allocated to process A. These next 3 units from 5 to 8 are empty, there is a hole, and then to B and C, then again we have empty, D, E, again we have empty. And how we keep track of these used units of the memory and empty units of the memory with the bitmap. We see this is the bitmap for this part of the memory. We see the first 5 units are being used, and in the bitmap we have 1, 1, 1, 1, 1. It means these 5 allocation units are being utilized by process A. Then 0, 0, 0, these next 3 units are empty. This is the way we keep track of the memory utilization with the help of bitmaps. The used allocation units are represented by 1, the unused or empty holes are represented by zeros. How do we manage the memory using the linked lists? Again, we have to refer to the same diagram. Let's see. This is how we do it with the linked list. P stands for a process, H stands for a hole. And we see here this H stands for hole, and this is from where the hole starts and what is the length of the hole. Similarly, we see here this is the process. It starts from 0 and length of the process is 5. We see this is process A, and it has the length is 5 allocation units. Next to process A we have H that starts from 5 and ends at 8, and it's the length of this unit is 3. We see here 1, 2, 3. Then we have a process which starts at 8 and the length is 6. The next process starts at 14 and the length of the process is 4. This is how we keep track of the linked lists. We keep track of the memory with the linked lists. How do we allocate and deallocate the memory? Let's take an example that there is a job, and that particular job can have a job on his left as well as on his right, or the process can have a job on the right and a left portion is empty, or the job can have another job on the left and right portion could be empty, or both flanks of the job could be empty. And once that job completes, how that memory is deallocated and becomes a part of the whole chunk, let's look at the diagram, how it is done. In this diagram we see before the X terminates, X is a job and it has another job on its left and on its right. At the second instance, we have a job A on its left and the right side is empty. Here at another instance, the left side is empty and right side is occupied by another job B. In the yet another instance, job X has empty slot on its left as well as on its right. Now, once the X completes, how it becomes a part of the remaining memory is shown here. In this part of the diagram, we see if X terminates or completes, then we have job on the left and right. If X completes and right side is empty, this creates this part of the memory available, and we have to keep track of that. And if our left side is empty, then we see we get this chunk of the memory available, and if there is no job on the left or right of the X, then we get this whole chunk of the memory available. Ladies and gentlemen, this very much wraps up our today's session, and in today's session we covered monoprogramming. We see how multiprogramming is modeled. We looked at multiprogramming with the fixed partitioning, multiprogramming with dynamic partitioning, memory management using bitmaps, and memory management using linked lists. With that, we conclude our today's session. Allah Hafiz.